Okay. Okay, so let me open the okay. So I should make a new file, right? Okay. So today we are going to do reaction rate and collision theory. Reaction rate and number one, number two, collision theory. And or then we are going to do Maxwell, because this is tough, so I'm going to cover this first. Maxwell-Boltzmann distribution curve. And number three, collision theory. It's very simple, collision theory, mostly theoretical. All right. However, the first 2 points are proper points. Okay. So
Yeah.
when we talk about the reaction rate, talking about the first point, I'm going to change reaction rate into rate of a reaction. Rate of a reaction. All right. So whenever a chemical reaction takes place, we determine the rate of a chemical reaction by the change in the concentration of reactant or a product. For example, we have a reaction A changes into B. Now, what is A? A is a reactant and B is a product. Now, Anika, you can measure rate in two ways. You can measure the rate in terms of reactants. You can measure rate in terms of product. However, because when the reaction takes place, the concentration of the reactant would decrease as the reaction progresses, right? And the concentration of the product would increase as the reaction progresses. Yeah. So you
Yeah.
can measure in both the ways that how fast one of the reactant is being used up, that how fast this reactant is used up, or how fast the product is being formed. Does it make sense?
Yes.
All right. So the rate could be rate is equal to, now be very careful. Let's suppose this, as I told you, this reactant is A and product is B. So when I'm going to find out the rate in terms of reactants, I'll write minus the concentration of A divided by the time, divided by the time. All right. So what is this? This means that the rate of the reaction in terms of reactants can be measured by measuring the change in the concentration of A divided by the change in time. It can also be written as minus small change over small change in time. All right. Now, why did I put this minus? Because the reactant is decreasing. All right. So what is the rate in terms of reactant? Change in the concentration of reactant per unit time. This is the proper definition of rate of the reaction. What is the formula? This is the formula. You can write rate of the reaction is change in the concentration, and by the way, concentration is represented by this big bracket. Change in the
Okay.
concentration of reactant divided by time for change to happen, or make it simple, divided by time taken, time taken to make that change. Does it make sense?
Yes.
Yeah, is it clear? So, and
Yes.
why did I put this minus? As I told you earlier, because with the passage of time, the concentration of the reactant would decrease. So that is why we are going to write like the change in the concentration of reactant per unit time. I hope it's clear, right? Okay. So,
Yes.
or time taken, or you can write change in time. Both are correct. Change in time. Now, if I'm going to write the rate in terms of product, I will write that change in the, this would be rate is equal to change in the concentration of product, which is B, divided by the change in time. So this would be the rate in terms of products. This would be the rate in terms of product. I didn't put the sign of positive because it is understood that if I'm putting a negative sign here and I'm not putting any sign here, that means it is positive. Is it clear?
Yes.
Any confusion?
No.
All right. So I'm going to write rate is change in the concentration of reactants slash products per unit time. It's entirely up to you whether you want to represent it in this form, whether you want to write in this form, number two, or whether you want to write in this form. It's entirely up to you. Is it clear?
Yeah.
Good.
Yes.
All right. Now I'm going to show you the graphical representation. Now, if I will show you a graphical representation, for that, I'm going to show you the slide afterwards. If I will draw a graph between concentration and time, and I am taking the concentration of the reactant, which is actually what? Which is A. So have a look. If I'm going to draw a graph, the graph would be, what do you think? If I will draw the graph in terms of reactants between concentration and time, what would be the shape of the graph? What do you expect? Sorry?
I'm just thinking.
Oh, okay. What,
Um,
Anika, what is happening to the reactant?
it's being used up.
So it means that the graph would go down or it would go up. Concentration.
Down.
Down. Well done. So this would be somewhat the shape of the graph.
Okay.
All right. So that means with the passage of the time, what is going to happen? The concentration of the A reactant would decrease. That means that the gradient is decreasing. All right. Okay.
Okay.
And by the way, it is touching the x-axis. So that means that gradient would be zero when the reaction is complete. Okay, now
Okay.
I'll show you the gradient. Just give me a minute, I'll show it from the slide. Now, if I am going to draw a graph between concentration of product, that is what? B. So concentration of B versus time, what do you expect? Uh, B is the product. So what do you expect?
It will increase.
Yes, the graph would be like this. Are you getting my point? Okay,
Yes.
so that means because the concentration of the product is increasing with the passage of time, so that is why I'm going to get the graph in this way, right? So now if I want to draw the tangent, I will draw on any point, I will make a tangent and then I can easily calculate the gradient. And if I
Yeah.
want to make a tangent on this graph, then the tangent would be like this, all right? And then I can easily make the take the gradient. Is it clear? And you know
Yes.
that the gradient is always y over x. Y
Okay.
over x. Y over x. All right. So the grade, if you are going to take the gradient in terms of reactant, then what is going to happen? The gradient decreases as the rate decreases and becomes zero when all of the reactant is used up. All right. And in the graph, this graph, we determine the rate of the reaction at point A. Let's suppose this is point A. So on point A, we can determine the rate by drawing a tangent and then making the gradient. So we determine the rate of the reaction at point A by drawing the tangent. I'll use another line. Look, this pink line. By drawing a tangent, this is the tangent, all right, to the curve at point A and then measuring its gradient, which is y over x. I hope it clearly makes sense.
Yes.
Yes. And now let's discuss the unit. Now, after finding out the gradient, whatever is the value of the gradient, that would be the value of the rate. All right. And as I told you earlier, that rate is change in the concentration of the reactant and change in time. So the concentration has a unit, mole per decimeter cube, and time is having a unit second. So what would be the unit of rate? Bring it up, it becomes mole dot dm minus cube dot s minus 1. So this is the unit for the rate. And how did I find it
Okay.
out? By dividing these two things. Because I know that the unit of concentration is mole per decimeter cube and unit for time is second. So when I divide these two, I am going to get this unit if I am going to bring this up. So mole dot dm minus cube dot s minus 1 is the unit for the rate. Is it clear?
Yes.
Okay,
Yes.
right. Now I am going to stop sharing from here, and I'll move to the laptop and I'll show you the um, so here it is. Okay. Can you see this graphical determination of rate? I hope you can
Yes.
see the slide. All right.
Yes.
If you want it to be bigger, I can do this. I hope now you can easily see. Now,
Yes.
you can see, can you tell me that this rate has been determined by considering what? A reactant or product?
Um, reactant.
Reactant. Why? Because the graph is declining, Anika. The graph is going down. So that means that the concentration of the reactant is being used up. Yeah?
Yes.
All right. So just concentrate on the graph, right? The if you see that it has been started from 1.80, all right, and then it goes down, and it ends at almost 0.50. Yeah. And
Yes.
now you can draw a tangent, the rate, now rate calculation. The rate of the reaction at any moment can be found from the gradient of the tangent at the point. The steeper the gradient, the faster the rate of the reaction. All right, now I'm going to show you. Have a look here. Can you see? Now place a rule on it is written on the right side. Place a rule on the outside of the curve and draw a line as shown on the graph. So this is the tangent. Is it clear? Now, if you
Yes.
will even read this value, now have a look. Can you see the triangle has been formed like this line, then this line, and then this line. Can you see it's a triangle like this?
Yes.
Yeah, I hope you are getting it. Yeah, Anika?
Yeah.
All
Yeah.
right. So you can see this is the triangle being made, right? On the bottom right side, this is gradient is a blue triangle, right? Now I am going to do it on the graph. Look, this line and this line, and then it goes up. So the triangle has been formed. So what is the value? This is the value on y-axis. This is y-axis. I hope you understand this is y-axis, right? The
Yes.
value is 1.60
Yes.
divided by 1520, which is the time. Yeah,
Yes.
1520 on the x-axis. So have a look. Please check this gray box. That is, gradient would be minus 1.60. Where did I take minus 1.60? From here, from the y-axis. Because the gradient is y over x. Yes, Anika, the gradient is y over x. Can you see the bottom blue triangle? Yeah, right angle triangle.
Yes.
Y over x. So what is taken on y? Concentration. What is taken on x?
Time.
Time. Well done. So y over x. So that means I need to divide concentration by time. I did this and I got the rate. And the rate is negative because the reaction is slowing down. I hope it clearly makes sense.
Yes.
Good. Now, have a look. It doesn't mean that you can only draw a tangent here. You can draw a tangent anywhere and you can take the gradient. Look, you can take the
Yes.
here, 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 or here. So you can draw the tangent anywhere and then you can you see the yellow triangles I have made?
Yes.
Yeah. So by these, by using these triangles, you can calculate the gradient, and whatever is the value of gradient, that would be the value of rate of the reaction. Clear?
Yeah.
Good. Now, the only thing I need to add is about the initial rate. Now, what is initial rate? This is given in red, right? But this is laptop, so I can't circle it. I can only move the arrow over it, right?
Mhm.
Okay, initial rate. Now, how to calculate the initial rate? If you are going to make a tangent at t is equal to 0, that will be the initial rate, right?
Yes.
So the new word I am adding is the initial rate. The rate calculated when time is 0, that is called as the initial rate. So if you are going to divide 1.80 by what? By this,
0.
by 0, then what you are going to get? You are going to get the initial rate. Does it make sense?
Yes.
Good. So first I told you about the rate, the definition, the formula, and then the representation. And then we discussed how the rate can be graphically calculated. Then we saw it in terms of reactants. Then we made it in terms of products. And then we drew the tangent. And then we found the gradient, and the value of the gradient actually gives the value of the rate. Yeah, so that's
Yes.
about it. So I just wanted to show you these two, three pictures, and one more picture right in the beginning. This one, this one. So have a look here. Rate change during a reaction. You can see few lines on the graph. Yeah. So
Yeah.
if you check A and B, the red and the blue lines, they are going down, and the C line is going up in a form of a parabola. Yeah. So A and B, that means that A and B are the reactants. So the reactants A and B, the concentration decreases with time. And product, which is C here, the concentration of this product is increasing. You can see if you are going to make a line with the ruler, you will end up here. Am I right? On the y-axis you will end up
Yes.
here. So this would be the concentration of the product would be formed. And if you are going to find it in terms of A and B, then you need to look with the passage of time, the rate is, the concentration is declining. So if you are going to find out the rate, it would be negative. However, one more point I want to tell you, that can you see that B is steeper as compared to A?
Yes.
Yeah. So that means that rate with respect to B is concentration of B is faster, because the steeper the curve, the faster the rate of the reaction. So we have two reactants, A and B. Then what does it mean? That A is also used up, but B is being used up fast. So the rate
Okay.
of the reaction with respect to B would be faster as compared to A. Why? The curve is steeper. The
Okay.
curve is steeper. Yes? All right. Now, this is all about the rate. We have covered rate. All right. Now we are going to move to the next one, that is about the collision theory. But before starting that, have a look again. Just read this slide. In a reaction such as A plus 2B changes into C, the concentration might change as reactant A and B concentration decreases with time. product concentration increases with time. The steeper the curve, the faster the rate of the reaction. Reaction starts off quickly because of the greater likelihood of collision. I'm going to move to the second topic, that is collision. Reaction slows down with time as there are fewer reactants to collide. So when the reactants would be used up, then definitely the reaction will slow down because there is no more reactant to be reacted. Yeah.
Okay.
Right. Now, I hope, Anika, you have understood. I hope the pace is fine for you. You have understood it clearly.
Yes.
If there is any ambiguity, you may ask, please.
No, I understand.
All right, fine. So now I am going to stop the. Okay, I'm stop sharing from here. That's about it. And I am going to leave as well because this is what I wanted to teach you from the graph. All right. Okay, now uh, I'll share the screen. Okay. Yes, Anika, can you see the screen?
Yes.
All right. Now the second point on your which you have highlighted, that is the collision theory. Yeah, am I right?
Yes.
All right. So the first of all, I think there is a brief discussion about the factors affecting the rate of the reaction, if I'm not wrong. Have you highlighted that as well?
I do think that is coming up in the test. Let me check.
Yes. Okay.
Oh yeah, in terms of the effect of changing concentration, temperature,
Yeah.
pressure, and surface area.
Yes. Yeah. So I'm going to discuss that with you as well,
Okay.
right? All right. So the rate of factors affecting the rate of reaction. Now, there are few factors which can affect the rate of the reaction. The very first factor is the effect of concentration. Number one, the effect of concentration. Now, increasing the concentration of the reactant, what do you think? If I'm going to increase the concentration of reactant, what is going to happen to the rate? Rate will also increase. The rate of reaction will also increase. That means there is a direct relationship between the concentration and the rate of the reaction. So an increase in concentration often causes an increase in the reaction rate. All right. So what
Yes.
happens actually for many reactions, if the constant, look, Anika, let's suppose this is a vessel and there are four molecules. This is the concentration of four reactants in it. All right. Now, definitely they are going to collide with each other and they will try to produce the product. Now, instead of having four reactants, if I have 10 or 11 reactants, what do you think? More product would be formed or less product would be formed?
More.
More, because if you are going to increase the concentration of the reactant, more product would be formed. For example, Anika, you must have watched that game in which you have to that is of bumping cars. Yeah. So
Oh
what do you
yes.
think? If bumping cars would be less in number, there would be less chances of collision with each other. If there would be more bumping cars in that area, there would be greater chances of collision. Yeah.
Yes.
So that means that greater, if we are going to increase the concentration of the reactant, the rate of the reaction would also increase. Why? Because more product will be formed. Why? Because more collision will take place.
Okay.
All right, try to digest it. If something is bothering you, I am going to discuss it with you.
No, I understand.
All right, good. So, for example, uh, um, if I'm going to, let's suppose, if I take, um if I draw a graph, let's suppose, now giving you the example from this. Oh dear. Right, like this. Let's suppose I am doing a reaction. Now you will tell me, right? Now I am doing a reaction of calcium carbonate with hydrochloric acid. And you know that I'm going to get cut it in two parts from here and here. So I'm going to get CaCl2 plus CO2 plus H2O. Now, what do you think? I have a fixed amount of calcium carbonate, right? Now I am getting a graph of volume of carbon dioxide here and time here, right?
Yeah.
Now, if let's suppose I have two curves, you will explain these curves to me. This is for A and this is curve B. There you are. Now, what can you tell me about this graph?
Um, they both have the same like end point of reaction. They have the same volume of CO2 at the end.
Absolutely correct. What else?
Um, they both start with the same volume of CO2.
Okay, what else? If I'm going to highlight what I want you to think about. Now, what do you think?
Um,
Which curve is
line
steeper?
A.
Well
Yes, the
done.
curve A is steeper.
The curve is steeper in line A, yeah?
Yes.
Steeper curve. What does it mean?
Um, faster rate of reaction.
Why? Good. Why? Faster rate. Why?
Um, there's a greater volume of CO2, so there's more collisions.
You need to talk in terms of the concentration.
Oh, so there's more
Yeah.
concentration of CO2.
More carbon. Now, listen, Anika, you were absolutely right when you told that curve A is steeper. Fine. You said that it shows that it has a faster rate. Absolutely correct. It means that the volume of carbon dioxide initially will be collected. The initial volume of carbon dioxide collected will be greater or faster, although the curve meets at the end, right? So why it is
Yes.
faster? Because the concentration of the acid was greater. So that is why the volume of carbon dioxide was very high in the beginning. Is it clear? So
Okay.
curve A represents the higher concentration of the acid. All right. So you will
Yeah.
notice that the gradient. Now, if I am going to draw a gradient, don't you think that the gradient of curve A is always greater than the gradient of curve B?
Yes.
Yes, well done. And that curve A levels off before the curve A levels off before curve B. That means both of these factors indicate that the rate of the reaction is greater for the higher concentration of the acid. Now, actually, if you are going to use, because calcium carbonate is fixed, I'm keeping it fixed. So, if you are going to take a high concentration of HCl, then this graph will be produced because high concentration of acid will produce a greater volume of carbon dioxide in the beginning. But
Yeah.
because calcium carbonate is fixed, then only the carbon volume of carbon dioxide, which is finally produced, would be the same. Why? Because calcium carbonate is fixed. Now, if
Yeah.
I will repeat the experiment, I'll take the same amount of calcium carbonate, but this time I will take lesser concentrate or lesser concentration of the acid. That means less concentration, or it is dilute. That means it is not very concentrated. So if I will take a less concentration of the acid, then the volume produced would be the same, but the reaction would be slow. Why?
Mm.
Because the acid is weak. But
Okay.
uh, in the end, the volume of carbon dioxide produced would be the same. I'm repeating again and again. The volume of the carbon dioxide produced would be the same towards the end because calcium carbonate is fixed.
Yes.
So are you getting my point? So that means
Yes.
these two lines, they are because of the concentration of the acid being used. I hope it's clear.
Yes.
All right. Can you please tell me what is shown in the graph? What is your intake for this?
Um, curve A has a steeper gradient than curve B,
Hmm.
um, because there's a greater concentration of carbon dioxide as the concentration of hydrochloric acid in the reactants was greater than in curve B than curve A than curve B, but they
Yes.
both produce the same volume at the end and level off at the same point because the volume of calcium carbonate is fixed.
Excellent work. So I hope that you can easily, if it comes in the paper, you can easily tell that what's the difference between the two. Steeper curve, higher gradient. Lower curve, lower gradient. Number one. I'm repeating. Steeper curve, high gradient, more carbon dioxide initially, and one thing more, high concentration of the acid used. Yeah.
Yeah,
Then this lower curve, lower gradient. That means that the concentration of the HCl was lower. But because the volume of calcium, because the amount of calcium carbonate was fixed, so the volume produced would be the same towards the end. I hope it's clear.
yes,
Should we go further along? All right,
yes.
good. Now we are going to discuss the effect of and you can also, by the way, you can also discuss in terms of collision, because more concentration means like this. More concentration means more particles. More particle means more collision. More collision means more products. Should I write this? More
Okay.
No, it's not clear.
No, I understand.
All right. More concentration means more particles. More particles means more collision. More collision means more product. More product means steeper curve. More product or quick product. Instead of more product, I'll write product forms quickly. Right, like this. The volume of carbon dioxide is far greater here. And then
Yeah.
the gradient would also be higher, right? Now comes the second point, that is the um, effect of temperature. It's quite a lot actually, Anika, and it's confusing as well. Effect of
Mm.
temperature. So I have to explain each and every bit of it. All right, effect of temperature. Now, what do you think, Anika? If you are going to increase the temperature, what is going to happen?
Will increase the rate of reaction.
Yeah, because you know that let's suppose if you have put something on stove, let's suppose you put water in a pan on the stove. All right. Now, if the gas is lower or less gas is coming out or the flame is lower, then it will take longer time to boil off the water. Yeah, and
Yes.
if the flame is higher, then it would take less time to boil off the water. So what happens actually, because when you increase the temperature, what happens? The kinetic energy of the molecule increases. When the kinetic energy is increased, they start colliding faster with each other. And when they start colliding faster, then in case of boiling of water, they are not producing any product. But if you are, let's suppose, if you are boiling eggs in water, so if the flame is higher, then you are going to get the product quickly, that is boiled eggs. Yeah. And
Okay.
if the flame would be lower, then it will take more time to boil the eggs. So what happens actually that when you increase the temperature, the average kinetic energy of the molecule increases. They collide with each other faster and they produce the product quickly. All right. So they
Yes.
produce, and the rate also increases. So if you're increasing the temperature, increases the rate of all the reactions, and because the frequency, what is increases the frequency of collision increases. The frequency of collision of what? Of particles increases, and the energy of collision of particle increases. Is it clear? So
Yeah.
that is why the rate will also increase. So may I write that it is directly proportional to rate, that increasing the temperature increases the rate. And same here, that the concentration is directly proportional to the rate, that increasing the concentration increases the rate. I hope it clearly makes sense. If something is bothering you, please, you may ask.
No, I understand.
All right. Now comes well done. Now the third one is the effect of pressure. Actually, these are three big topics. The first one is we have already done the rate of the reaction, the factors affecting the rate, then comes collision theory, and then comes Maxwell-Boltzmann distribution curve. I'll try my level best to complete all of them today, right? The effect of pressure. So when we talk about the pressure, you know that the molecules, they collide with each other. All right. So if, let's suppose, the molecules are far apart. Now, if I am going to apply the pressure with the help of a piston and it goes down, then what is going to happen? And this would be the volume. Now, all these particles, I'll rub these, and all these particles would now be where? In this space, in this much space. Six particles. So there is, what do you think? There is a more chance of collision?
Yes.
There is a greater chances of collision, right? So the explanation is actually similar to that for concentration. If the pressure of the gaseous mixture is increased, there will be more reactant molecules in a given volume of the mixture. So the frequency of collision will increase, with the result in the increase in the rate of the reaction. Got my point?
Yes.
Should I repeat?
Sure.
All right, I'm repeating. The explanation would be the same as for the concentration. If the look, Anika, first the molecules were in the whole vessel. They were far apart from each other. But when I applied pressure on it with the help of a piston, and now when I apply pressure, so this much would be the volume now. So the particles
Yes.
would squeeze in, the particle would squeeze in, and when they would squeeze in, they are going to collide more with each other. So when they will collide
Yes.
more, the rate of the reaction would increase. Yeah.
Yes.
And this is for, now the effect of pressure is only for the gaseous reactions, not for the solid or liquid. Gaseous reaction, for
Okay.
example, N2 plus 3H2 mix up to NH3. Now, nitrogen is a gas, hydrogen is a gas, ammonia is a gas. So yes, for this reaction, the effect of pressure would definitely be considered. All right. However, changing the pressure has virtually no effect. Changing the pressure, changing the pressure would have no effect on the reactions in the solid or liquid phase. Why? Any idea?
Um, because you can't squash a liquid or
Well
solid.
done. Well done. This is because the volume of solid and liquids change very, very little if you are going to put them under pressure. So the particles, they do not move closer together because as you said, you can't squash them, right? So the effect of pressure will only be considered for the gaseous reactions. All right. Now the next one. I hope it clearly makes sense, whatever we are discussing.
Yes.
All right. The effect, if you feel any ambiguity or any problem or some point is not clear, feel free to ask. The
Yeah.
effect of surface area. Now, you must have seen it in normal life, in normal routine life. For example, let's suppose you want to mix sugar in water, all right, and you know that sugar is in the form of crystals. So if you are mixing 3 tablespoons of sugar in a jug, it would take some time, but if you grind that sugar and make a powder of that sugar of the same 3 tablespoons, and if you try to mix the powdered 3 tablespoon sugar in a separate jug of water, you can quickly mix it. Yes or no?
Yes.
Yeah. So what does it mean? That means it means that if you take something in a form of lump, it will take some time to react. But if you are going to take the same thing in powdered form, it will react quickly. Yeah. Okay. So that means
Yes.
that if um, uh, the collision, let's suppose if you have magnesium reacts with HCl. Now it is going to form MgCl2 plus H2. Now this is the balanced equation, right? So you are producing hydrogen gas and you are using magnesium and hydrochloric acid. Now, magnesium is a metal in the form of strips. Yeah. So if you are
Yeah.
going to dip a strip of magnesium in acid, it is going to react. Definitely, it is going to react, but it will take some time. But if you, instead of having the strip, if you take the same amount of water, same vessel, and instead of having the strip, if you have powdered magnesium, the surface area is increased and hydrogen is given off more quickly.
Okay.
Yeah. All right. For this, I'll give you the example. If you take this much block, that is the strip, and then you divide it. Now, where can the acid react? 1, 2, 3, 4. On these 4 sides, acid could react. Yeah.
Yeah.
Now, if I divide it, if I make a powder of it, if I'll make a powder of it, now look how many small particles I am getting. Are you getting my point? Now, what
Yeah.
is going to happen? Acid will react from all sides.
Okay.
So that means that the rate of the reaction would increase. Can you see I have only made 1, 2, 3, 4, 5, 6, 7, 8 small particles. Look how quickly acid can react on each particle. And as compared to this, there are only 4 points from where the acid could react on this lump. If I rub this, then there are only 4 points on which acid could react. This side, this side, this side, and this side. What about this? Acid cannot react because it is in the center. Now, if I
Yeah.
divide it in different parts, acid can surround each and every bit of the particle. So the rate of the reaction increases if the surface area increases. So when I grind this strip into fine powder, I am increasing the surface area. Are you getting it?
Yes.
So by increasing the surface area, the rate of the reaction increases. I hope it clearly makes sense. Yes.
Yes.
Now, the next one is catalyst. Catalyst. It's also there in your syllabus, the effect of catalyst.
Think
Kindly
so.
check. Yeah. And light as well. Yeah. The effect of
I
catalyst. Yeah.
and
The
what was the
light
other
is
one you said?
light. The effect of catalyst and the effect of light.
I don't think light is, but I think catalyst is.
All right, so I'm going to discuss only catalyst. Yeah, because light, if I'm going to discuss light, it will be about the colorimeter. It is going to take a lot of time. So the effect of catalyst. Now, you know
I
what?
don't think I think catalyst is on my spec, but it's not on the highlighted points.
All right, then should we leave it?
Yeah, I don't think it's going to come up on the test.
All right, fine. Now, so we are going to move to the collision theory now. Yeah.
I only need to know, sorry, I only need to know the catalyst in terms of understanding the Maxwell-Boltzmann distribution.
All right, fine, fine. Okay. Okay.
Okay.
So I'm going to tell you about the Maxwell-Boltzmann distribution curve as well. But let's do collision theory, and then we will do the Maxwell-Boltzmann distribution curve. Collision theory. There are three important points when we talk about a collision theory. Let's suppose we have two reactants, A and B, and they form by the way, Anika, I'm not asking frequent questions from you because I have to cover three topics, right? So if I'll
That's
ask
okay.
question, yeah, okay, fine. All right. These are the reactants. These are the reactants, and these are the products. Now, collision theory says that the product will not be formed until and unless A and B they collide with each other. All right. So the very first point of collision theory is the particles must collide with each other. This is the first point. The particles must collide with each other. Now, number 2 point. Now, let's suppose if the two particles, they are colliding, but they are not colliding with enough energy, then the products will not form. So even if they are colliding with each other, the product will not be formed because they are not colliding with sufficient energy. All right. So what is that second point? The two molecules like this, A and B, the two molecules must collide with sufficient energy. For example, let's suppose, let me give you a daily life example. Anika, you have an apple. Yeah, you want to cut the apple, right? You have got a knife in your hand. All right. Now you apply a very little pressure on it. Do you think you would be able to cut a knife, to cut an apple?
No.
No, no. All right. So if you will apply greater pressure, then this knife would go down and it would cut the apple in two halves. Are you getting my point?
Yes.
Yeah, so that means you have to apply enough energy to cut the apple. Same is the case here.
Yes.
The molecules, even if they are colliding, but they are not colliding with sufficient energy, then they will never be able to form the products. All right. And yes, clear?
Yes, I understand.
And okay, good. And what that sufficient energy is? Activation energy. Now, what is an activation energy? It is the minimum amount of energy which is needed to start a reaction. That is called as activation energy. All right. So this definition is really important. So I hope always keep this knife in mind whenever you are thinking about the activation energy, no matter how sharp the knife is. But if you are simply lightly putting it on the apple will not be cut. But when you
Okay.
apply pressure and you use some of your energy on this sharp knife, then it will slide down and it will cut the apple in two parts, right? Now,
Okay.
the first point, second point, now third point, that is or correct orientation. What is the meaning of correct orientation? That means the reaction will only take place when the molecules they collide with each other in correct or proper orientation. Now, what is proper orientation? Let's suppose we have this is ethene. This is ethene. You know, it reacts with HBr, right? Now, this is one molecule and this is another molecule. Let's suppose they are going, the very first point, they need to collide with each other. And now, what is the product being formed? This is the product being formed. H, Br. Br and H. Now, this product will form number one when the particles they collide with each other. That means when ethene molecules or particles collide with HBr molecule. Even after fulfilling the first condition, even then the reaction will not be successful. What is the next condition? When they collide with each other, they must collide with the sufficient energy, and that energy is called as activation energy. So they must have the proper energy so that when the collision will take place, that collision is fruitful collision. Fruitful collision. Okay, good. Now, both the conditions have been fulfilled. What conditions? The particles will collide. Okay, they collide with enough activation energy. Okay, still, this product will not produce until and unless they collide in proper orientation. Now, how this collision can be done? Have a look quickly. Now, look, this is C double bond C H H H and H. Now HBr will collide like this. HBr on this double bond from H side. Okay. Now the
Okay.
second option. C H H H and H. Now it is going to collide, but like this HBr. Now Br side will collide with this double bond. All right. Now the third option. The HBr molecule will collide in this way with this H. So this collision, H with the double bond, second Br with the double bond, and third H with H. Now, if this orientation would be there, the product, this alkyl halide will be formed. If Br will collide with the double bond, no product will form. If H of the HBr will collide with the H of the ethene, no product will be formed. Why? This is not a correct orientation. This is not a correct orientation. What is the correct orientation? When hydrogen collide with the double bond. Why? Because bromine is a very big molecule. When it collides with the double bond, it is going to knock it off. No, they are not going to collide with each other with proper force. This is very big, this is very small. In this case, this is small, this is small. So this is the perfect match. In this case, the H is colliding with H, with both are small, but the product will only be formed when H collides with the double bond. So it is not colliding with the double bond. Does it make sense?
Yes.
All right. Now, there is another point about the steric hindrance. The steric hindrance is the same thing. Let me write this word. Steric hindrance. Steric hindrance is again that, for example, if you remember, I have taught you this. This is tertiary alkyl halide, right? When sodium hydroxide, yeah, or hydroxide, a nucleophile is going to attack on this carbocation, it cannot attack. Why? Because this carbon is surrounded by big molecules. So OH cannot it cannot make it way into this carbon, electrophilic carbon. It cannot make its way because this is this side is being obstructed. No invasion can be done because of the steric hindrance. So how this OH approaches the electrophilic carbon atom? That first of all, before this thing, this bond gets broken. And then we get a carbocation like this. And now this side is open. Now OH can attack on this electrophilic carbon atom. So until unless a carbocation is formed, the reaction will never happen. So this is called as steric hindrance. Does it make sense?
Yes.
Right. I know that I am very fast right now because I have to cover everything and I'm left with very little time, right? So
Don't worry, I'm
should
not
I?
finding it fast.
I have a next class actually at 10 o'clock.
Okay.
So if possible, do you, because now it's 9:59, so what should I do? I won't be able to finish it. Do you have some other time in which we can do it?
Um,
Next week?
it's okay, because I just needed it for my test tomorrow, but that's okay, don't worry.
All right, fine. Okay, I'll simply tell you within 2-3 minutes whatever I can tell you about the Maxwell-Boltzmann distribution curve. This is
Okay,
the
thank you.
welcome. This is the Maxwell-Boltzmann distribution curve. That is fraction of molecules with given energy, and this is the molecular energy. Now, at any given temperature, average kinetic energy of the molecule is constant. But different molecules, they possess different energies. That means that the distribution of molecular energy is not normal. Some molecules may have very high energy and some have very low energy. So Maxwell-Boltzmann, they made a curve that is for the distribution of molecular energy at a given temperature. So let's have a look. This is the graph of molecular energy. The area, and what is this is the activation energy. I'll use a different color. That means these molecules which can pass the energy barrier, they are going to make the product. Now,
Okay.
all these molecules which are under this curve at a specific temperature, they cannot pass the barrier. Have a look, right? Are you getting my point? So let's
Yeah.
suppose they are 80 and they are 20. The total molecules were 80 plus 20, 100. Out of 100, how many have passed the energy barrier? Only 20. Are you, yeah? Because this is activation
Yes.
energy. The molecules which are present after the activation energy, that means these are the molecules which possess the energy to have a fruitful collision and to make the
Okay.
product. These molecules cannot make the product. Why? Because their molecular energy is less.
Okay.
All right. Now let's suppose it is at temperature T1. All right. Now be very careful. You will give me the answer. And as soon as you'll give me the answer, you'll come to know whether you have understood it or not. Now there is another curve like this. Now, this is T2. Now, can you tell me that which one is greater? T1 is greater than T2 or T2 is greater than T1?
Isn't T1 greater because the curve is higher, so there's more temperature?
Okay, now, but Anika, have you noticed that these are the molecules which can pass the energy barrier when the temperature is T1? But
Okay.
when I increase the temperature, the molecules passing the energy barrier, it gets doubled. So that
Okay.
means that T2 is greater than T1 because the curve is shifted more towards the right. And when it is shifted more, then the proportion of the molecules passing the energy barrier increases almost double. Almost
Okay, that
double.
makes sense.
So, yeah, good. And by the way, area under both the curve is the same. The area under both the curve is the same. What does it mean? Do you remember we took 100 molecules for T1? Yeah.
Yes.
And 80 couldn't pass the energy barrier, and only 20 passed the energy barrier. For
Yeah.
T2, we have again 100 molecules, but now 40 will pass the energy barrier and 60 will not pass the energy barrier.
Okay.
Got it? And for T1,
Yes.
have a look. For T1, um, uh, I'll write 60 here. Sorry, I wrote it at the wrong place. Just a minute. Yes. Now, listen again. This is the second curve. Now, while discussing T1, which is the lower temperature, if we have 100 molecules, 80 molecules couldn't, oh dear, 80 molecules couldn't pass the energy barrier, only 20 could pass the energy barrier. But when I increase the temperature, T2, then the molecules would remain 100, but now 40 will pass the energy barrier and 60 will not pass the energy barrier.
Okay,
Are
that
you
makes
getting my
sense.
point? All right.
Yes.
And apparently, it looks like this is high. Actually, this is not high because more molecules are under the curve which do not pass the energy barrier.
Okay.
And at high temperature, less molecules are under the curve which couldn't pass the energy barrier. And greater
Yes.
molecules can pass the energy barrier. I hope it makes
Okay.
sense. Yeah?
Yeah.
I have tried my level best to explain it as quickly as possible in the most methodical way, but I hope you must have understood somewhat of it. Yeah?
Yes, I understand. Thank you.
All right. Okay. Thank you so very much, Anika.
Thank you. Bye.
Okay. Bye.
Bye.